Well, welcome back. I have a nice quick video hopefully for you tonight. And this is just kind of a real-world application review of increasing and decreasing. And we'll hit on all sorts of functions that increase, decrease, and then talk about increasing and decreasing at the greatest rates. So buckle up, here we go. Alright, let's go ahead and start by drawing an increasing function at a constant rate. So let's just break those two words down. Increasing obviously means your function is going up from left to right. And at a constant rate means that the slopes are all the same. So basically, I would say this function is increasing. If I walk on it, it's going up, it's increasing at a constant rate. Basically, what I'm trying to instill here is that the slope at this point, the slope at this point, the slope at this point, they're all the exact same. So what does that tell me about f prime and f double prime? Well, clearly, if my function's increasing, I know f prime is greater than 0. I also know that it is a constant. Okay, so for example, my slope could be 2. My slope could be 8. It is a constant. Therefore, its second derivative is equal to 0. Let's try decreasing at a constant rate. Again, this part is telling me that my function is decreasing if I were to walk on it from left to right. At a constant rate, obviously meaning that my slopes are the same. So here, this function is decreasing at a constant rate. Again, my slopes here, 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 and here, they're all the same. So because my function's decreasing, f prime is less than 0, and again is still a constant. Therefore, f double prime, again, is equal to 0. Our next function is increasing at an increasing rate. Alright, well think about what that looks like. So again, I'm increasing, so this is implying that I'm going up, and my rates are getting larger. That means my rate, that four-letter word I refer to as my slopes, are getting larger. So you could think about it like this. Basically, clearly this function is increasing. If you walk on it, you're heading up. And if you start thinking about your slopes, pick a number that you think that slope could be. Maybe a half. Well, if you compare that to this slope, did that slope get steeper or less steep? I would say as I increase, my slopes are getting steeper. For example, 1/2, maybe that's a slope of 2, maybe that's a slope of 4, a slope of 7. My slopes are increasing. So f prime is greater than 0, and notice f double prime is also greater than 0. I just want to recall f double prime, I should be talking about the concavity. I need to be concave up. Decreasing at an increasing rate. So again, break it down. Decreasing means your function is going down. Okay, so it can be going down either concave up or concave down, but this time, an increasing rate again means that my slopes are getting larger. And if you're not sure, try to draw it two different ways. Let's say we think it looks like this. Let's just check our slopes. Now remember that these slopes are negative. So if I were to assign a number, I'd say that's pretty steep, maybe -7. This is less steep, maybe -4. Less steep, maybe -1, maybe -1/2 here. Notice actually these numbers are getting larger. Okay, if you think this is a very negative number, this is a less negative, so these slopes are getting larger. So this function is decreasing at an increasing rate because my slopes are getting larger. So I know f prime is less than 0, and f double prime, notice, is greater than 0. Again, I'm concave up. Two more to go here. Increasing, but at a decreasing rate. So again, I need my function to be going up, and I just have to worry about my concavity here. Let's take a look at this one. If I say I'm increasing, I think you could easily buy that. And now my rates have to be decreasing. Basically, again, I would just want to imply that rate means my slopes are decreasing. And again, if you don't believe me, just draw some tangent lines and assign some values to them. This is pretty steep. Maybe I'll say it's a slope of 6. This is less steep, maybe a 4, maybe a 1, maybe a 1/2, and eventually if I get to the top, it'll kind of flatten out and be 0. So my slopes are getting smaller, therefore they are at a decreasing rate. So notice my f prime is positive, I have positive slopes, but I'm concave down, so my second derivative is less than 0. And lastly, I need to be decreasing at a decreasing rate, and I would say it looks like that, and if you're not sure, just draw some tangent lines and ask yourself about them. I think the decreasing part, again, is obvious. If you walk on it, you're clearly walking down. And just assign some numbers to it. Again, it's negative. I would say maybe that's not very steep. Maybe a -1. This is steeper, so maybe a -2, maybe a -4, maybe a -9. Okay, so my slopes are getting smaller. And again, if for some reason you're stuck, picture 0 on the number line. If you get more negative, you are decreasing. So f prime is less than 0, and f double prime is clearly concave down, which is also less than 0. Alright, let f be a differentiable function that is strictly monotonic with no inflection points. Determine the signs of f prime and f double prime for the given tables, and then state whether f is increasing at an increasing rate, increasing at a decreasing rate, etc. So we just saw a question like this on the exam we took last Friday, I believe. So the first thing I can do is I'm just going to go through and determine whether my function's increasing or decreasing, and that should be fairly obvious just looking at my y values. 7, 10, 12, 13, I would definitely say this function is increasing. This guy, 3, 6, 11, 16, I would definitely say that's increasing. This one's certainly decreasing, and this function's decreasing. Now the question is, am I increasing at an increasing rate or a decreasing rate? Again, don't let that word rate scare you. When you see that 4-letter R word rate, it's just telling you to look at the slope. Now, you can't just do one slope and know if you're increasing or decreasing. You have to compare the slopes. Alright, so our goal is to compare the slopes to determine whether they're increasing at an increasing rate or at a decreasing rate. So let's look, 7 to 10. I'm going to do the slope formula. Change in y is 3 over change in x is 1. Slope formula here. Change in y is 2 over 1 and then 1 over 1. My slopes went from 3 to 2 to 1. So I would say that I'm increasing at a decreasing rate. Again, my slopes are getting smaller. The next guy. Change in y is 3 over the change in x. Change in y is 5 over the change in x. Change in y over change in x. Whoops, I subtracted. That should be 5/2. Alright, so let's compare them. Alright, I went from 1 1/2 to 1 2/3 to 2 1/2. Clearly, I'm getting larger. So I would say this is increasing at an increasing rate. We'll quickly run through the next two. My change in y is 5/2. Whoops, negative 5/2. Negative 4/2. And negative 2/2, which of course is negative 1, and that's negative 2. And I had negative 5/2 here. So, again, think about this. You went from negative, here's 0, you went from negative 5/2 to negative 2 to negative 1. Because these are negative, you're actually decreasing, but at an increasing rate. And lastly, you can run through it on your own there. Hopefully you can see that the slopes are decreasing at a decreasing rate. Next example. Traffic flow is defined as the rate at which automobiles pass through an intersection measured in automobiles per minute. The traffic flow at a particular intersection is modeled by the function f. Alright, so I just want to be clear about what this f is. F represents, it says, traffic flow. And we know that traffic flow is measured in automobiles per minute. Okay, now that means that traffic flow is a rate. I just want to be clear that this is a rate, and again, I know that because it's automobiles per minute. Part A says, is the traffic flow increasing or decreasing at t equals 3? So again, let's pull out those key calculus words. To me, what jumps out of the page is the words increasing or decreasing. Okay, when I see those words, that tells me to take a derivative. Now, who do I want the derivative of? Well, just read it. It says take the derivative of traffic flow. So since I want the derivative of traffic flow, and we've clearly identified f of t is traffic flow, I am taking the derivative of f at 3. Okay, so even though it was a derivative itself, it wants to know if that traffic flow is increasing or decreasing. So I am deriving traffic flow, which is f. So why don't we go ahead, we'll quickly pause it, go ahead and take your derivative and substitute in 3. So pause it, see what you get. So I know I got a little sloppy, I tried to squeeze it in here. I did my nice little chain rule both times, substituted in my 3, and I've got an answer of 1. So what that's telling me is since I got a positive derivative, I would say that my traffic flow is increasing because f prime of 3 is greater than 0. Part B. At t equals 3, so at that same time, is the traffic flow increasing at an increasing rate or increasing at a decreasing rate? Decreasing at an increasing rate or decreasing at a decreasing rate? Well, we already know from part A that the traffic flow is increasing. So these two I can already knock out. I already know that my traffic flow is increasing. Now I have to determine if it's increasing at an increasing rate or a decreasing rate. So this is telling me to take the second derivative. So let me restart with f prime of t. I recall, I think that was 2 times t plus 1 to the negative half plus pi sine pi t. And you can go ahead again, pause it, take your derivative at 3, and determine whether we're increasing at an increasing or decreasing rate. So again, I apologize for the sloppiness. I've got my derivative with my chain rule here, plugging in my 3. So I end up with negative 1/8 minus a pi squared, which is clearly a negative number. So I would finish this off by saying that the traffic flow is increasing because f prime is greater than 3, but at a decreasing rate because f double prime is less than 0. I'm sorry, I think I meant to say f prime is greater than 0, not 3. So really paying attention to who's given and what you want to do. Look for those key calculus terms, and that should give it away. Increasing or decreasing is calculus, and who am I doing it to? So in our next example here, I'm not necessarily certain that we need to solve it as much as we need to set it up and make sure we're looking at the same thing. So for example, for 0 to 30, the rate of change in the number of mosquitoes at time t is measured by this equation, which is measured in mosquitoes per day. Is the number of mosquitoes increasing or decreasing at time t equals 6? Alright, so really dive into and understand what m of t is. M of t is measured in mosquitoes per day, and this represents the rate in change of mosquitoes. So is the number of mosquitoes increasing or decreasing? So again, increasing, decreasing is telling me to take the derivative, and who do you want the derivative of? Well, I want the derivative of mosquitoes. Okay, what does m of t represent? Well, again, it represents the rate in change of mosquitoes, which is the derivative of mosquitoes. Okay, it already is the rate. So in this example, I don't need to actually take the derivative because m of t is the derivative of what I'm looking for. Okay, so again, in that previous example, we knew f of t was a derivative, but we wanted the derivative of that. In this example, I just want to know if the mosquitoes are increasing or decreasing. So I'm strictly looking at m of 6. And again, I'm not going to worry about the solving. I just want to worry about, do we know what function to plug it into? Part B, at t equals 6, is the number of mosquitoes increasing at an increasing rate, or etc. at a decreasing rate, decreasing at a decreasing rate, etc. Give a reason for your answer. Well, from our answer from number 6, which I'll just come out and tell you, we had 18 mosquitoes per day, okay, which tells me that my mosquitoes are increasing. I already know that my function is increasing. I now have to determine if it's at an increasing rate or at a decreasing rate. So now I need to take the derivative of m at 6. So I am looking for the derivative of m at 6. And again, I'm not so worried about the number as I am that you understand which thing you're taking the derivative of. Lastly here, the rate in calories per minute at which Mackenzie burns calories while running a race is modeled by this function. At what time is C increasing at its greatest rate? All right, so I see a few things in there. First of all, I want to know when C is increasing. So this increasing again is telling me to take the derivative of who? Of C. Now, because it says at its greatest rate, if you're the greatest at something, that means you are an absolute. And if you're the greatest, I would consider you an absolute max. So the first thing I'm going to start with is taking the derivative of C and finding my critical points. So C prime of t gets me negative t squared plus 11t. If I set that equal to 0, I can pull out a negative t. I've got t minus 11, so I've got t equals 0 and t equals 11. Quick sign chart, we know we're between 0 and 20. I've got my 11, my C prime describes C. If I plug those in, if I plug a 5 in, I get a positive. If I plug a 12 in, I get a negative. So I currently know that I am increasing on the interval 0 to 11. Now, do I exactly know where I'm increasing the greatest? Not yet. All right, in our list example here, we've got a lot to break down. So the rate in calories per minute at which Mackenzie burns calories while running a race is modeled by this function for 0 to 20. So let's just stop there. This represents the rate in calories per minute at which you're burning calories while running a race. At what time is C increasing at its greatest rate? I see two major concepts here. The first one is increasing, and the second one would be at its greatest rate. So let's just take them one by one. Let's talk about C increasing. This word increasing is telling me to take the derivative, and who do they want the derivative of? Who do they want to know is increasing? Well, that would be C. So I am finding C prime. And we can do that real quickly. Negative 3, how about negative t squared plus 11t? Set that equal to 0. I can pull out a negative t, and I've got t minus 11. So t equals 0, and t equals 11. Quick sign chart, obviously from 0 to 20, they told us. I've got t equals 11. C prime describing C. If I plug in a 2, I should get a positive, and if I plug in a 12, I should get a negative. That means that C is increasing on the interval 0 to 11. Now, that doesn't tell me where it's increasing at its greatest rate. It just tells me I'm increasing between 0 and 11. So, if my function might look something like this, I'm increasing from 0 to 11, then I decrease from 11 to 20. All I know is that it's happening sometime in here, and my goal is to find that time. Alright, now greatest rate. There's two huge keywords there, greatest and rate. When you see the word greatest, that means, you're the greatest. Nobody can be greater than you. You have to treat that, of course, as an absolute max. Now, more specifically, who do you want to be an absolute max? Well, it says, if you read the second word, the word rate. You want an absolute max of the rate of C. So I am looking for an absolute max of C prime. That means I need to take the derivative of C prime to figure out where this max is happening. So if I talk too fast for you, maybe slow it, rewind it, and make sure you really understand why we're picking the derivative of C prime. So C double prime of t equals negative 2t plus 11. Set that equal to 0. I've got t equals 11 halves. Quick check, 11 halves from 0 to 20. C double prime and C. If I plug a 1 in, I get a positive. If I plug a 19 in, I get a negative. Therefore, C is increasing at its greatest rate at t equals 11. Let me try to draw out a picture for you as well. If something is increasing at its greatest rate, I think it would look something like this. Clearly, would you agree that this function, well, I guess we'll say let's pretend this is 0 to 20 here. This function is increasing, and that's very obvious, the function's going up. Now, increasing at its greatest rate. Okay, basically, again, that word rate is telling me to look at these slopes. I want to see when it has the greatest slope, and by greatest, I probably mean steepest slope. So just think about it. If you were to draw a bunch of tangent lines, where do you have the steepest slope? I would definitely say some point around here it looks the steepest. All right? So think of it as, walking up a hill. Pretty easy, it's getting tougher, it's the steepest. Now it gets easier as you go on. So the slope is the steepest right here. Now you'll notice that happens to be a change in what? A change in concavity. All right, so that's another reason I'm looking at that second derivative to get my answer. Okay, when concavity changes and you have a point of inflection, you are increasing or decreasing at your greatest amount. Well, there you have it for a quick review. We'll look forward to seeing you tomorrow. Have a great night.